Good morning, everyone. Now let's have to continue with the network laws and theorems. This time we need to discuss Thevenin's theorem. What is Thevenin's theorem? It states that a linear two-terminal circuit which has several voltage or current sources and resistances can be replaced by an equivalent simple series circuit that contains one single voltage source. We call it as the VTH, and one resistance. We call it as the RTH. Let's consider this circuit as shown, and assuming that the unknown here is the current through the RL. There are two independent voltage sources, E1 and E2, with their internal resistances R1 and R2. These two independent voltages are supplying the load RL. Okay, in actual situation, RL is variable or it's not constant. If we change the value of the RL, we need to conduct another network analysis or circuit analysis to find for IL. And to avoid it, we need to use the Thevenin equivalent circuit, which is a simple series circuit that contains the VTH and the RTH, excluding the RL. So this is now the Thevenin equivalent circuit. We have a new value of the voltage, and we call it as the VTH, and another internal resistance of the source voltage, which is the RTH now. And then we connected back the RL since the unknown is the current in the resistor RL. In this case, when the value of the RL is changed, so it's not difficult to find for another value of the IL. We just simply use the Ohm's law. So at this terminal A, B, it is where we connect back the RL. And IL simply is just equal to, by Ohm's law, it's just equal to VTH divided by RTH plus RL. So if we change the value of the RL, so easily we can determine the IL by using Ohm's law. So let's define the VTH is the voltage at the open circuited terminals, and the RTH is the equivalent resistance at the open circuited terminals. And sometimes we call it as the looking back resistance. RL is the load resistance, and I is the current through the load, or we have here IL. So the main concern here is how to determine the voltage VH and the resistance TH. So let's have these following tips. First, if we solve the RTH, then these are the tips in solving for the RTH. First is we have to remove RL and leave the terminals open. Second, set all the independent sources to 0. Recall that the independent voltage source is replaced by a short circuit when we set it to 0, and the current source is replaced by an open circuit. Letter C, solve the equivalent resistance at the open circuited terminals. And that equivalent resistance, we call it the RTH. Second, how to find for the VTH. First, we remove the load RL only and leave the terminals open. Take note that in this case, in solving for the VTH, all independent sources are all together in a circuit. And after removing the RL, solve for the voltage at the open circuited terminals using any theorems that we discussed, since the circuit consists of more than one source. The source could be a voltage or a current source. Let's consider this circuit shown. And we need to convert this circuit into a simple series circuit that contains the VTH and RTH, or we call it as the Thevenin equivalent circuit. Let's recall how to solve or to determine the RTH. So first is we have to remove the RL and leave the terminals open and set all the independent sources to 0. Okay, so we have to first step 1, solve RTH, the RTH value excluding the value of the RL. So let's remove. So we have the terminals A, B where the RL is connected. So we have to remove the RL here. And then we have to connect back the R1, and the source voltage is to be replaced by a short circuit. That is how we set the voltage source to 0. Okay, so this is now the equivalent circuit. And we need to solve the R equivalent circuit at the open circuited terminals, and we call it as the RTH. So if we simplify the circuit, the R1 is just connected in parallel with the open circuited terminals AB, where we solve for the RTH as well as the R2. So what is then RTH? RTH is the equivalent resistance at the open circuited terminals AB. So since we see here that R1 and R2 are just connected in parallel across the terminals AB, so RTH, or the equivalent resistance at the open circuited terminals, will be 1 over 1 over R1 plus 1 over R2. Or you have to simplify it, the product divided by the sum, R1 plus R2. Okay, this is now the value of the RTH at the open circuited terminals, excluding the value of RL. Second step, we need to solve for step 2. Solve for the VTH. So if we go back, how to solve for the VTH? We just simply remove the RL only. And take note that all independent sources are still in the circuit, are all connected together in a circuit. And then we will solve the voltage at the open circuited terminals. Okay, so we have to remove the load resistance at the terminals AB, and then we connect. We have still the E1 and E2 in the circuit since we are trying to solve for the voltage. So we have R1, R2, and this is E2. So at the open circuited terminals, we have here EO. And how are we going to solve for EO at the terminals AB? Since there are two sources, and if we notice here that of course, there is no current at the open circuited terminals. So the current can flow from E1 to E2, and the same current that flows through R1 and R2 since they are now connected in series. So if we call the current here as I, and we will use KVL to solve, use KVL to solve I. Okay, so we have E1 minus I times the sum of R1 and R2 minus E2 equals 0. So solving for I, so we transpose it to the right side, then we have E1 minus E2 over R1 and R2. Okay, the unknown here is not the I, but we need I in solving for the EO. So in solving for the EO, then it's either we will be using the right loop or the other loop here. So if we will label, so we have here the A, B, C, this is C, D. And of course, this is the B. Okay, so at loop A, C, D, B, A. Okay, now what is the sign of the EO? If we go back to our circuit, the current here is going downward, so it leaves plus and minus here. So if we disconnect the RL, the terminal A is plus and the terminal B is minus. So we will be using this sign plus at A and minus at B in writing the voltage equation. So let's start with the EO at terminal A. So you have plus EO. Again, the voltage at the open circuited terminals, we call it as the EO or the VTH. So EO, so we have EO since it's open circuited terminals. Though there is no current, but there is a voltage at the open circuited terminals. So again, so we have plus EO in a clockwise direction and then minus I R2. Since the current that flows through the R2 is to the right, so you have here plus minus, and then next element is the E2 minus E2. That is equal to 0. So EO will then be equal to E2 plus I times R2. So what is the value of I? So we just have to solve I whenever we are given with the values of the voltages and resistances. Or if you want to use the left loop, this one that we encircled in black. So if we have here E, F, okay, so at loop, we will follow the direction of the current, which is clockwise. So we have loop A, B, E, F, A. So E, A, B, E, F back to A. So let's write and let's have to begin it at the AB. So since clockwise direction and we are getting the sign of the B. So you have minus EO plus E1 minus I times R1 equals 0. Since the current is flowing in this direction and we have here plus and minus of the R1. Okay, and then solving for EO. So we have EO then is equal to E1 minus I times R1. Okay. Take note here, then the VTH is equal to EO. Since the VTH is the voltage across the open circuited terminals. Then after solving for RTH and VTH, then we have to draw the Thevenin equivalent circuit, which is a simple series circuit now. So we have a new value of the VTH, the RTH, and we will connect back the RL, since the current in the RL is the unknown, and that current is IL. And then we simply use the Ohm's law to solve for IL, and that is VTH over RTH plus RL.